Hey, welcome back to Fan Mama Physics! In this video, 4.5, we are going to look at more examples of how to interpolate, extrapolate from a graph. So in this version, I will go through these examples just from observing the graph, using lines and kind of reading off your x and y axes. So it's the basic, it's the what you need for grade 9 math. Okay, so let's get going. Example 1, using interpolation to solve problems. Jenna borrows money from her parents for a school trip. Some of you don't need to borrow money from parents. She repays the loan after making regular weekly payments. Must be some very expensive trip. $200. Oh, okay. The graph shows how the money is paid over time. The data are discrete because payments are made every week. So it's not like every second, every day, every minute, every second of the week, Jenna is slowly feeding money to her parents. It's, okay, after 1 week, she gives a lump sum. After another week, she gets a lump sum, and so forth. Which is why this is a discrete data set, meaning every point in between weeks, so the time in between weeks, she's not making any payments. So it's just bloop, blop, 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 bit of money to her parents. Okay, so let's start with A. How much money did Jenna, or Yenna, however you like to pronounce that name, originally borrowed? So originally, meaning that this is before she started making payments. This is before all the weeks began happening. So at the very beginning of time, where weeks, the time is 0, so week number 0, this is where we have to read the graph in order to figure out how much she paid. So if we go to the beginning of time, which is 0 weeks, you can see that the graph, there's a data point here at 200. You have to ignore this box. I don't know quite why it is there. But sure, let me draw the line better so you know exactly which line we are talking about. It is this one here. Okay, so ignore the other line there. In fact, let me just put in a different color so you know exactly what I mean. Okay, so we can see based off of this line that the graph intersects or touches $200 at the beginning of time. So she originally borrowed $200 at T or time week number 0. Okay? All right, so that's it. No calculations involved. But just keep a notice on the dots. The red dots are probably the data points, the discrete values. How much money does she still owe after 3 weeks? So again, you just go to the graph and read it. At 3 weeks, it is right here. So that's, no, oh no, this is 3 weeks. Whoop. So 3 weeks, we go up to the graph here. It intersects this point on the graph, so then we move over to the y-axis to figure out the corresponding match. Matching the y-axis there, that is, it's in between 120 and 160. Between 120 and 160 is a difference of 40. So every box represents $20, which is $140. Okay? So she still owes, and this graph says, money owed, so this is $140 she still owes after 3 weeks. Lots of money. Hey, this is interesting because imagine, does she pay weekly? She makes regular weekly payments, so we can actually look at, just for curiosity, how much money she's paying every week. After the first week, she paid, it's 1 box worth. So from 20, halfway to 60 is 180. So she paid $20. Seems like she pays $20 a week. Interesting, hey? Okay, so that's B. C, how many weeks will it take Jenna to repay half of the money she borrowed? So if she owes $200, half the amount of that is going to be how much? You're right, it's going to be $100. So if we go to the graph, we look at, okay, $100 is going to be here. You move across to you look at where it intersects our line on the graph. Bam, intersects right there. So then to find the corresponding time, we have to move all the way down directly straight down to the x-axis to figure out the time. That is 5 weeks. Okay, and that's how much. So then you can think about it, well, if it takes 5 weeks to pay half, then it must take another 5 weeks to pay the other half. That means after 10 weeks, she would have paid off everything. So if you take a look at the graph, bam, the graph intersects here. She will owe $0 after 10 weeks. Here's a question for you. Does it make sense for this graph line to keep going like I've shown over here? Pause the video to make a thought, to think about it. If you're thinking, no, it doesn't make sense for the graph to continue, then you have a point, because that just means, well, I mean, unless Jenna really, really wants to pay her parents money because she loves paying her parents, then sure, the graph can keep going, and if she still continues at the same rate, then what does this mean? After 12 weeks, she would have paid another amount, this much, which is $40. This is -20. This is -40. Oh, very good. You notice that the graph starts to go into the negative region. Then what do you think that means? It means not only she's no longer owing her parents money. So what is it? What's the opposite of owing? Opposite of owing is, I guess, you have a credit. So it's almost as if she's paying her parents so that her parents can save her money up. So instead of owing, it's more like saving your money. So that's the part where the graph would go into. If it keeps going, that's kind of what it would mean. Does it make sense? It could. It depends on what Yenna wants to do, right? So absolutely, if you keep extending this graph, that could be what it means. If I go back, let's say I extend the graph backwards in time. So 0 weeks and then, I don't know, -1 week, -2 weeks. Does that make sense? Pause the video and give it a thought. Okay, if you think it doesn't make sense, you do have a point there, because it doesn't say anywhere in the question that Yenna borrowed more money than $200. And it's not like that, so it's almost as if the money that she owed started off at 0 weeks and it kept moving from there. It doesn't make sense for time to kind of go backwards, because she borrowed no other sum of money from her parents. So this is the type of thinking you want to think about when you're interpreting your graphs. Okay, so that was interpolation for you. Next up, we have extrapolation on this next example. So, you know what? If you want to try this graph, might be a good time to pause the video. Okay, so I am going to do this question here, using extrapolation to solve problems. Maya jogs on a running track. The graph shows how far she jogs in 10 minutes. And yes, it does. It goes all the way to 10 minutes. Assume Maya continues to jog at the same average speed. So basically, imagine the graph continues to show this linear relationship and forever and forever and forever. Predict how long it will take Maya to jog 2,000 meters. Ooh, okay, very interesting. So notice that this graph has gone way beyond the space that we are given. It says how far Maya would jog in 14 minutes. What assumption did you make? Okay, so it's going to be a little bit tricky from here. Because we only know how far she jogs in 10 minutes. But hey, let's do something. Let's do a quick calculation here. In 10 minutes, she jogs 1,200. So let me write this down. In 10 minutes, she travels 1,200 meters, okay? And assuming this is her average speed and it's not going to change, the rate stays the same, so she's not speeding up or slowing down, she's maintaining this speed for a very long time. So, in fact, we might be able to use this to our advantage. And what we're going to do is we're going to use this rate that's given to us in the graph. 10 minutes, she travels 1,200 meters. So maybe we can find out how far she travels in 1 minute. So to do that, you're right. If I want to find how far she travels in 1 minute, I have to take the distance that she travels divided by divided by time, meaning I'm going to get 120 meters. She's going to travel 120 meters in 1 minute. Okay, this is interesting because I can then use this one to maybe first of all answer question B. Okay, it's because I need to find how far she travels in 14 minutes. If she travels 120 meters in 1 minute, that means to find out how much she travels in 14 minutes, I have to multiply my distance of 120 by 14 minutes. And I am going to get 1,680 meters. So this is interesting because the graph space is so small. It is impossible for me to draw the line, to continue drawing a line for us to figure out where it intersects the y and x axes. We kind of have to grab whatever information we can from the graph and kind of work our way from there. Now we're going to do A, because A is a little bit trickier. Now we know that in 1 minute, Maya travels 120 meters. I'm going to use my pen to model that. So imagine my pen is the distance that she travels in 1 minute. I need to figure out how many minutes she needs to travel. For her to travel 1,200 meters. No, sorry, 2,000 meters, not. So what I want to do is I want to see how many times my 120 meters goes into the 2,000 meters to see how many minutes it takes her to travel the 2,000 meters. Okay, so that just means that if I need to figure out how many minutes it will take her, I need to divide the 120 meters per minute into 2,000 to see how many times 120 meters goes into 2,000. So what that looks like is I have 2,000 meters divided by 120 meters per minute. And I use this big slash sign to signify division. So on my calculator, I put 2,000 divided by 120, and that's going to give me a very ugly number, but that's okay. I have 16.66 repeated minutes, and I just put a bar on top to signify that it's repeating. Okay, so that is kind of how I would have to juggle with this question without there being graph space. Okay, you kind of have to get the information from the graph and use it. Last question, what assumption did you make? Now, when we extrapolate data from a graph, we kind of have to assume that the pattern continues to go in the linear relationship as shown. If it deviates from that straight line, then our extrapolation would not make sense because we assume that the pattern continues. The pattern for this graph is Maya's jogging speed. Notice I used her jogging speed in question A and B. If her jogging speed changes, then my prediction for A and B would be false. So the assumption that I made here was that her pattern of jogging maintained the same. To be more specific, Maya's average speed stayed the same. And this is assuming even after 10 minutes, she still maintains this average speed. So that's how we can figure out A and B. For example 3, I'm going to make this a separate video, okay? So good for you for staying along with example 1 and 2. I will see you next time on example 3. And I promise it will be a shorter video. So thank you for watching. Stay tuned. Fan Mama Physics signing out.